systems, and I think now also in the discussions yesterday, they all have a common core of ideas and they tend to implement them in different ways. And I guess Bpipe is one of those solutions that I looked at initially and which I liked for its simplicity. So I hope I can make the argument that Bpipe, for some applications at least, is a very interesting concept or a different, interesting framework to work with. So for us, when we started evaluating pipeline frameworks or workflow management systems, were a couple of things that this kind of system needed to fulfill. Requirements. It needed to have minimal overhead when developing. I don't like spending a lot of time writing lots of code to get very simple things done. It should be flexible, ideally modular. So if you start developing pipelines, it would be nice if you could reuse parts of pipelines and combine them in different ways to make other kinds of pipelines. It should be portable. That was partly a requirement because we have our own cluster, but we also want to run things on Höppner. Höppner uses Slurm, we use LSF. So having something that makes this kind of transition easy is always a benefit then. We wanted an efficient translation of the pipeline graph to one or more viewing systems. That also came from discussions both internally and with Höppner that people or bioinformatics users tend not to think about that core hours cost money. So there are very simple pipelines like implemented in Bash or Make or so on that would just, book an entire node, then run half of the pipeline as a full node job and then other parts as single core jobs. So having a system that does this in an elegant and efficient way would be a benefit. It should be robust, fault tolerant, and it should have checkpointing, so like any build application like Make or Snake Make, so essentially it should be able to resume at failed stages, should kind of tell us what went wrong and keep a record of what went wrong. And ideally it's open source, so not depending too much on external support, or at least the ability for us to contribute or request features. So Bpipe is so I'm calling it a pipeline interpreter and a runner. So it basically has this dual functionality. You can define workflows and you can run them. It's written in Java and Groovy. So Groovy is a scripting language that belongs to the Java ecosystem. So Johan mentioned Scala is a more lightweight version of Java. Groovy is even more lightweight than that. So if you come from Python or Perl, then Groovy will feel very familiar, yet you have access to the entire Java ecosystem. But you don't actually need to know Groovy to work with Bpipe, and I hope I can make that clear. So Bpipe essentially reads easy to write instructions and constructs from these instructions a dependency graph, which then can be run locally on your local machine or on all major queuing systems. So it supports LSF, Grid Engine, Slurm, Torque. And getting new support is actually fairly easy, so they have documentation if you need a new queuing system. Getting that implemented is stupidly easy. As I said, it supports parallelism and checkpointing. It has a very neat audit trail, so it creates a folder in which it keeps a record of everything that it has done. You can always go into that folder if you need to debug your pipelines. So, and finally, Bpipe, the program, and the pipelines themselves are completely portable. Nothing needs to be compiled. It's basically just text in the Java drop-in application. You can run it anywhere without any sort of previous effort. So as I said, nothing needs to be compiled, just plain text files. Bpipe is open source, and it's available on GitHub. Right, so what does that look like? So kind of going back to the very basic example of a Hello World application, this was also shown this morning. Basically, Bpipe has a pipeline instruction, and in this case we have stages. The stages are called Hello and World, and in each of these stages we have an execute command. So this kind of can be a script that you call, could be a shell command, could be something else. Anything that can be executed and that produces an output. This is then run using this fairly simple syntax. So then you execute from command line Bpipe run the name of your pipeline, and then in this case it will print Hello World to the screen, which is simple enough. Right, so looking at a more bioinformatics related example, so here we have, for example, aligning short reads against the genome sequence, transforming that into a SAM file, and then doing something with the SAM file, in this case sorting the SAM file to create a sorted output. And that's kind of how we could implement that in the Bpipe pipeline. We have one stage that we call align. This stage calls two consecutive executes, so two commands are executed one after the other. And then we have a second stage that we call sort that implements the sorting function. right? Again, we can call this just Bpipe run or pipeline, and it will produce the sorted output. The problem here is that, of course, we have hard-coded names. We don't want that. Otherwise, we have to change it for every time we want to run the pipeline. So then what Bpipe does, it has reserved variables. One is called input, and one is called output. And these variables are essentially passed between the stages. So something that comes into a stage is called the input. Something that is then defined as the output is passed on to the next stage in the workflow. Again, we can run this, and it will produce, in this case, a sorted output. And you will already know that the name of this file is named after the stages that are being run. This behavior can be changed, but it's kind of a built-in feature that Bpipe has. Right, so I'm here highlighting how the information flows through the pipeline or through the workflow. We have an input. In this case, it's a short read file. We create an output. That output is passed on to the next stage where it becomes the input here in green, and then the final output in orange. And that is kind of how the product is being constructed. So essentially what Bpipe does, it has an implicit input and output. Essentially you can throw in any sort of file that is being considered the input, and then that file moves through your workflow, going from input to output, and then in the end you get your product. So there's no command line flags or any sort of specific variables for the different stages. Bpipe does all of this implicitly. So as I said, every operation or every stage has things going in and has things coming out. And the name of the output is basically implicitly through the stages, or if you want to have specific names, you can also do that with reserved functions. So essentially what that means is that Bpipe is a highly modular framework. So each stage, each processing that you do can be contained in its own module, and how you then build a workflow is just connecting the modules in different ways based on what your desired processing chain is. So basically, generating pipelines can be broken down into two things: coding of the stages of the modules, basically calling a read aligner, indexing a BAM file, quantifying reads from the BAM file, and so on, and then combining these modules into whatever sort of workflow you want to do. So here basically it's just showing we have three modules that we can just simply chain like this, and then it would be a serialized workflow. The only problem that Bpipe currently has, and I should mention this, is that the modules themselves are not telling you what they expect to come in and what they tell you what is going out. So you need to be able to keep track of what you do. I hope that this will be improved in the future. There are some tricks that you can employ to make sure that at least the module checks whether it gets the right kind of data, but it will not tell you in advance. So a word on parallelism. There's many scenarios in how we might want to parallelize data on a cluster or even on a single compute system. Here we have one example. We have many input streams. This is, for example, if you analyze RNA-seq data from 10 different conditions and you want to run the pipeline on all of these 10 conditions in one go rather than having to submit 10 different jobs. So basically, Bpipe supports wildcards, where you have a percentage sign that corresponds to the shared part of the file name that groups more than one file together into one stream. In this case, sample 1, sample 2, and sample 3. And then you have a wildcard symbol that basically then determines what are the variable parts of the common files. In this case, it's 1, 2, 1, 2. And that will basically create 3 independent pipeline runs or streams, one for each of these paired end samples running some kind of RNA sequencing pipeline that you then have to define. The second thing is that you have a job that is branching. We haven't seen this too much, so essentially, assume you have your RNA-seq pipeline. You might want to perform some sort of filtering on the read file. You want to trim off adapter sequences, and then you want to have one branch that produces some kind of statistics, but also passes this on to an alignment stage and a quantification stage. Maybe from the alignment stage, you also want to store variables. Bpipe does this in a fairly simple way. If you have ever seen phylogenetic trees, for example, in biology, you can just write out the different modules or stages you want to run, and then by using square brackets, you can group the different stages into their branches. So basically, what this will do is it will perform the trimming, and once the trimming is done, it will create the align branch, and then parallel, since it's kind of in square brackets, will do the align and quantification branch, and group with these two we have the statistics, so that will be branched off earlier. The good thing is that Bpipe has the graphical option, so once you have written your pipeline, you can get that printed out as a file, as a graphic file, and then you can just see, okay, did I actually get it right? And it also has a graphical editor. And finally, what Johan referred to as kind of splitting and merging files. So that's also supported by Bpipe. Bpipe can, for example, we have a FASTA file or a FASTQ file that we want to split into 10 chunks so that we can run it on 10 nodes in parallel. That is being implemented by whatever sort of program you want to use for splitting. And then by using a wildcard here, so basically everything that comes out of the split stage is to be passed on to the align stage. And then basically after this has run, you can merge them back together into one stream using this very simple syntax. So one quick word on queuing system or resource usage. That's kind of very important in bioinformatics, I think. Bpipe has many ways of doing this. You can either specify for each of your stages what that stage is supposed to be used in terms of, for example, CPU cores. You can hard code that, which at the end of the day is of course not a very good idea. You can also refer to it from the command line. You can say my pipeline is allowed to run at most at 8 cores and then use a reserved variable called threads. Or what we are going to do in the exercises today, it has a reserved config file name called bpipe.config, which it will read. And here we specify that we run on Slurm. We use this kind of queue. That's our account number we want to build things to. The standard job can run for 10 minutes, but for example, the align stage can run for 20 minutes and uses 8 processing cores. So you can be very, very granular about what the different jobs in your pipeline use in terms of resources. You can even specify the runtime based on the file size that you put in. So if you have different file sizes, you can say, you can basically compute a sensible wall time based on that file size. Right. So then finally, variables. Say you have a genome sequence you want to align against. So you not only have this implicit input-output, you can also specify variables that are then used by the pipeline. For example, here, the path to the genome sequence that you can either code together with the pipeline. You can also call it from another file. So in this case, we code all our variables in the config file. Bpipe will then read that config file through the syntax. So you can neatly separate the actual logic of the pipeline with the different things that have to go into the pipeline. Right. So in all of these components put together, so essentially there are four elements to Bpipe. One is our collection of modules that we can use then, very similar to how Galaxy does it. You have this kind of a library of things, and you can then just quickly put them together to build all kinds of different pipelines. You can have your pipeline instructions in a separate file, so if you have the same pipeline, you don't need to actually edit the pipeline logic. You can do that per pipeline run within your config file. All right, here's rather, this actually workflow instruction. Here's the pipeline config. So this you never have to change. You can change the things that you need to access through a separate config file or from the command line. We also talk about this in the tutorials. And finally, Bpipe has a very kind of separated way of interacting with queuing systems, so you can have the same pipeline with the same modules running on Slurm, LSF, or whatever, just by changing this single file for your pipeline. So summaries. Bpipe is highly modular, it's completely platform independent, which at least to me is a great advantage. It's very easy to learn. It's implemented in Groovy, but most of Bpipe is really just, you don't have to know any programming. It has a very kind of condensed down syntax. The only time where you ever want to use Groovy is if you in some way need to interfere with Bpipe's built-in functions. So say you have a behavior, like a program kind of produces an output that is not properly modeled by Bpipe's built-in functions, then you might have to kind of resort to doing some Groovy to kind of pop the hood and kind of rewire things. But most of the time this will not be necessary. So the kind of the overhead is really minimal in that sense. It's very fault tolerant, does checkpointing, and like any build tool like Make or SnakeMake, it can resume. If you change a file, it will know that this file was changed and only rerun the things that depend on that file. And it has very easy and efficient integration to any sort of compute infrastructure, at least for the major queuing systems like Slurm, LSF, or Grid Engine. Right, any questions? Or probably maybe afterwards.